Operation Teapot, the latest addition to our Encyclopedia of Nuclear Testing, bears the dateline Spring 1955. For the fifth time in continental testing, the symbol of nuclear power rose over the mountains of Nevada. This series encompassed so many objectives that preparations began while there was still snow on the mountains surrounding the Nevada test site and in the valley north of Yucca Flat. In contrast, the series came to an end in May amid the bloom of desert flowers. 14 times during that period, the blinking blue light on the pole above Camp Mercury indicated the shot was on for the following day. Although the 7 programs conducted by the Military Effects Group included some 50 different projects and participated in all 14 shots, the most important military effects studies were concerned primarily with 3 shots: an underground, a tower, and a high-altitude burst. The S, or underground shot, was scheduled to extend our knowledge of the cratering efficiency of nuclear weapons. In 1951, the first underground nuclear shot was fired during the Jangle series. Yield 1.2 kilotons. Depth of charge 17 feet. The apparent crater had a radius of 130 feet and a depth of 53 feet. The true crater was never measured. Therefore, on Teapot, a new technique was planned to determine the depth and diameter of the true crater. To permit correlation with the Jangle U results, a device with the same yield, 1.2 kilotons, was chosen, and the shot point was located near the old Jangle U crater, but at a sufficient distance to ensure against any interaction. Vertical holes 8 inches in diameter were drilled into the ground in a straight line bisecting ground zero. Sand mixed with a colored dye was poured into each hole, red, yellow, and black respectively. 3 holes, including the one at ground zero, were at a depth of 200 feet. Additional holes were dug, varying in depth from 150 to 50 feet, for a total of 21 holes, the outermost being 350 feet from ground zero. After the burst, when the soil has cooled radioactively in 6 to 8 months, the remains of these colored columns will be excavated, the dimensions of the true crater established, and the zone of rupture defined. At ground zero, or rather under ground zero, a weapon hole 11 feet in diameter was dug to a depth of 70 feet to permit a charge depth of 67 feet. It was expected that this depth might produce a change in the TNT cratering equivalence of the nuclear charge, with consequent revision of the scaling curves for underground shots as extrapolated from the Jangle results. In addition, it was hoped that further data could be established on the relationship between atomic detonations and high explosive tests in Nevada soil. With such a relationship confirmed, HE tests could be made in other soils at various depths to be representative of the target applications throughout the world. The actual digging of the hole and the placement of the weapon also served as a stockpile to target sequence test of ADM, or atomic demolition munitions. ADM would have great use in barrier systems or retardation operations to destroy airfields, dams, bridges, tunnels, mines, underground structures, or to create large craters as obstacles. And as a basis for training, studies were made of the problems encountered in planting such king-sized land mines. Estimates of the time required to hole out such a device were substantially confirmed. Secondary objectives of the underground shot were to obtain additional data on fallout and residual radiation, base surge, ground shock and air blast, and earth shock loading. Studies of radiation on this shot were especially significant because of the immense amounts of soil that would be contaminated and dispersed over the surrounding terrain, both from the base surge and fallout. Collectors and samplers, badges and dosimeters were set out before the burst at locations predetermined by the wind forecast. Those in hot areas were set out on trailers attached to long lengths of cable so they could be hauled out safely. The objective was to determine the distribution and intensity of fallout and to plot isodose rate contours on the radiation field as a factor of time. Transient surface and underground phenomena measurements included air blast, earth pressure, acceleration, and strain, all as functions of time over a range of 200 to 600 feet from ground zero. A number of flexible measuring devices were installed at a depth of 15 feet at a ground range of 300 feet to determine basic earth loading data for more efficient design of underground structures. Also, studies were made with modified dugway boxes to correlate the results with previous findings from small HE charges and the Jangle underground shot. After arming and insertion, the backfill of the main emplacement shaft and the access shaft was exceedingly well tamped to eliminate any surrounding air spaces. H hour was 1230 hours on 23 March. As expected, the base surge phenomenon was clearly visible. The throwout reached a height of 700 feet and a maximum diameter of 1,300 yards. The diameter of the base surge extended beyond 1,760 yards and definitely carried radioactivity of high intensity in the upwind and crosswind directions. Time of arrival data downwind from ground zero show that the fallout traveled at about 2 miles per hour ground speed. Cloud growth studies indicated a maximum height of 10,500 feet at 10 minutes after detonation. Radiation surveys were made by lowering an instrument from a helicopter over the crater at H+1 hour and 40 minutes. Calculations indicated that the dose rate had been 6,000 Roentgens per hour at H+1 hour, just inside the crater lip and extending out to 150 feet on all sides of the crater. 90% of the activity on the crater lip was in the first 12 inches of depth. In general, good correlation was noted between the gamma field intensities as predicted from HE and nuclear data and the observed intensities. Using the T to the -1.2 decay factor, a plot of distribution and intensity of fallout at H+1 hour showed almost 1/10 of a square mile enclosed by the 3,000 Roentgens per hour line, almost half a square mile at 500 Roentgens per hour, and about 1 1/4 square miles at 100 Roentgens per hour. The 20 Roentgens per hour area reached about 4 miles downwind. Samples of the soil in the fallout area, analyzed by a scintillation spectrometer, revealed that the residual gamma spectra were predominantly those of fission products with small amounts of neutron-induced activities in manganese-56 and sodium-24. Since ground personnel might be required to pass through or occupy an area in which there is fallout, a study was made of the nature of the radiation hazard. Human phantoms were set out in radioactive areas. Some in prone positions, some in standing positions, and some in areas that had been brushed superficially to determine the value of such a simple precaution. Results indicate that the surface dose from soft gamma or beta radiation in many cases was 20 times the average internal dose for a man lying prone, but that brushing the ground reduced this factor by 50%. Data from instrumentation on earth shock revealed that while inputs were lower than expected, nevertheless satisfactory measurements were obtained on transient surface and underground phenomena. Aerial mapping techniques were used to measure the apparent crater for comparison at a later date with dimensions of the true crater. From aerial stereographs, the depth of the apparent crater was computed at 90 feet, the maximum lip height at 19 feet, and the radius at 146 feet. The radius was less than expected. These results indicate that the charge depth does not appreciably increase crater radius, although the volume of material displaced is greater. An analysis of the data from the Jangle and the Teapot underground shots of identical yield leads to the conclusion that there is no significant change in cratering TNT efficiency over the range of charge depths from 17 to 67 feet for a yield of 1.2 kilotons. South of the underground testing area is Yucca Flat, location of Hornet, a 300-foot tower shot. Although Hornet was a development shot, a military effects study was made to evaluate the attenuating factor of a ground smoke screen against thermal radiation. As expected, it was found that a 75 to 90% attenuation resulted in areas where the fog oil smoke was heaviest. Out on Frenchman Flat, however, the Teapot schedule called for the most extensive military effects test of the series, coded as the Met shot. A tower shot of 28 kilotons expected yield, 400 feet above the dry lake, Met involved the greatest number of projects in two important objectives. First, destructive loads on aircraft in flight, wherein 3 drone jet aircraft were timed to be directly above ground zero at shock arrival time. And second, a study of the behavior of blast waves along different types of ground surfaces, particularly to obtain more information about precursor phenomena. Several low nuclear bursts on prior Nevada tests had revealed the existence of a precursor or non-ideal blast wave that preceded the main shock front. Shot 10 of Upshot Knothole formed such a wave, and drag-type targets were damaged much more heavily than by similar overpressures from Shot 9, which had an ideal waveform. For example, on Upshot Knothole, jeeps were exposed in both shots 9 and 10 to overpressures of approximately 9 psi. On shot 9, only moderate damage. On shot 10, a low burst, the damage was extremely severe, in many cases completely demolishing the vehicles at the same overpressure that produced moderate damage on shot 9, a high burst. Dynamic pressures were much higher for the low burst, which produced a dust-laden precursor blast wave. Was dust an important factor? Did the precursor increase the damage effectiveness of a low burst? Would a low precursor forming burst?
The Footage Archive YouTube channel is a place where you can find historic footage from world history. Subscribe to take a trip back in time.